and you'll find a vast, wide open space. There are no walls dividing the room and no columns interrupting the floor plan. Look at this 3D wireframe of the building directly above that ceiling. Stacked up there are 40 floors of residential apartments, forming a dense, heavy grid of load-bearing walls and columns pressing downward. Notice how the vertical supports in this diagram simply stop before they reach the lobby. The columns carrying 40 floors of structure above do not exist down here. The weight of the building hasn't vanished. Hundreds of thousands of kilonewtons of gravity load are still pushing down, and all of that physical force has to reach the foundations without crushing the open space below. Mixed-use towers have to stack completely different types of physical spaces on top of one another within a single footprint. This diagram shows a typical residential level. Apartments and bedrooms require tight, repetitive structural supports, placing columns every 4 to 6 meters. Drop down to the parking podium below, and the geometry changes. To fit vehicles side by side, a car park needs a wider grid, spacing columns 7.5 to 8.4 meters apart. The two systems do not line up. Then, at the very bottom, retail spaces and lobbies demand an entirely open layout with 0 columns. Because you cannot physically extend any single column grid straight down through all 3 layers, a hidden structural mechanism has to bridge the gaps between them. Without it, the upper floors would have nothing to stand on. That mechanism is the transfer structure. It is a massive, heavily reinforced concrete element that catches the load from the upper grids and redistributes it to the supports below. Watch the force lines on this cross-section. By the time a single column in a 40-story tower reaches the transfer level, it can carry 20,000 to 30,000 kilonewtons of gravity load. That is the equivalent of 3,000 fully loaded family cars pressing down on a single point on this beam. The structure functions exactly like a bridge. The concentrated vertical force hits the beam, converts into immense bending and shear forces, travels horizontally through the concrete, and safely redirects down into the offset columns below. Absorbing that severe bottleneck of weight requires transfer slabs up to 900 millimeters thick and transfer beams up to 3 meters deep. They are consistently the largest and heaviest concrete elements poured in the entire building. Building one of these elements on an active site is incredibly difficult. Before the concrete cures, a beam of this size is far too heavy to support its own wet weight. This graphic illustrates the temporary propping system required. To keep the wet transfer structure suspended, engineers install thick steel props extending down through 3 to 5 completed floor plates to carry the load all the way to the foundation. Then there is the steel. The interior of the formwork is packed with multiple layers of large-diameter reinforcement bars. It is so densely congested that placing and vibrating the concrete through the gaps requires a highly coordinated pour plan. Every embedment and starter bar has to be positioned with extreme precision. A 20mm misalignment in a normal floor slab is a manageable error. Make that same 20mm mistake in a transfer slab, and you create a severe structural defect that propagates up through 40 floors. Once the pour begins, it can run continuously for 12 hours, triggering a violent chemical reaction known as the heat of hydration. This cross-section tracks the thermal gradient inside the beam. The sheer volume of curing concrete creates a massive temperature spike in the core, while the outside surface cools rapidly. If that temperature differential isn't carefully monitored and controlled, the thermal stress will crack the element from the inside out. Constructing a transfer structure is a highly monitored, high-stakes battle against gravity, geometry, and chemistry. When the construction dust settles and the building opens, all of that engineering friction disappears into the walls. The tight residential grid, the wide parking podium, and the column-free hotel ballroom all operate flawlessly, stacked right on top of one another within the exact same footprint. Without the capacity to catch and shift those forces, every high-rise would be locked into a single, repetitive structural grid from the foundation to the roof, dictating the layout of every floor. The immense technical difficulty of designing and pouring these heavily reinforced elements is the necessary price developers pay for three-dimensional architectural freedom. Millions of people walk under transfer structures every day without ever noticing they exist, but they are up there, silently catching the vanishing columns and carrying the weight of the entire vertical city. Walk into the ground floor lobby of a modern high-rise,